Hello and welcome. This is Electricity and Magnetism video lecture part 1. Today I'm going to talk about electric charges and electric fields. This will be an introduction and some basic calculations about electric fields and forces, how to calculate them for a given distribution, for instance. So there's a lot of historical background in the book, going all the way back to Greeks, and talks about Benjamin Franklin and his experiments and all that. Basically, okay, so let's make a plan here. Let's start with the idea of electric charge. Okay, so its history goes back to Greeks. And that's something which you can experience in your daily life too, right? On a dry day, you walk on a carpet and then you touch the doorknob, you feel a shock, right? Or you comb your hair and then take the comb and bring it next to some paper or something, it attracts, right? So you know what electricity is, static electricity. And people have known about this for a long time, like they would rub some glass against silk. You know, we have a piece of silk and let's say a glass tube or a rod. Okay, so you rub it and then you can observe the electrostatic effects with these, let's say, glass. And you can even experiment with them, like silk and glass, and then how about some fur and plastic. Okay, you rub it, and then you could observe static electricity. But if you're careful, you'll quickly realize that the properties of these materials, I mean the glass and the plastic, after you rub them with silk and fur, are a little different. Suppose you bring two such pieces of glass, you bring them together, you'll see that they will repel each other. Repel. But if you bring the glass piece next to the plastic, they will attract each other. So there's this polarity, this dual nature, let's say, attract. Okay, so it was first Benjamin Franklin who actually theorized this, who saw this dual nature of electric charges and their interaction. And he called these charges. So the word charge, namely positive and negative charges, we owe this to Benjamin Franklin. This is the 18th century. Now I'm going to explain why this happens, okay? Why we have this. Why do we have sometimes attraction, sometimes repulsion? But to continue our timeline here, after Benjamin Franklin and with his experiment with the lightning and the kite and all that, people discovered electricity, you know, batteries and light bulbs and all that, you know, the 19th century developments in physics. An important milestone, I guess, would be James Clerk Maxwell, who built up the foundations of electromagnetic theory. Okay, so for a long time, people knew about electric charges, but they didn't know anything about magnets, or let's say they didn't know the connection between magnetism and these electric charges. It was Maxwell who combined the two and came up with a solid theory of electromagnetism. magnetism. Okay, so these two are actually one and the same. That's why we call it an electromagnetic force or electromagnetic interaction, which is a fundamental force of nature. Now, when Benjamin Franklin came up with this idea of charges, electric charges, he said that these two objects, like the two glass pieces after rubbing with silk, had the same charge, let's say positive charge. And the rule was positive charges would repel each other. And when you tried the glass with the plastic, of course, back then they didn't have plastics, but they had some other material. Since they attracted each other, he said this should be a different charge, maybe a negative charge. And the rule is if you have opposite charges, you will have attraction between the two objects. If you had two negative charges, they would also repel. All right, so like charges repel, opposite charges attract. But he didn't really know, I'm talking about Benjamin Franklin, he didn't really know why these charges existed in the first place, okay? And we now don't know that matter is made of atoms, and an atom is basically a positively charged nucleus and negatively charged electrons around the nucleus. And the thing that makes the nucleus a positive charge is this particle called proton. Proton is a positively charged particle, and electron is a negatively charged particle. And according to this rule of opposite charges attracting each other, there's an interaction between the proton and electron. They attract each other. That's why we have a stable atom, or an electron is attracted by a proton. So, of course, Benjamin Franklin didn't know anything about atoms and electrons and protons. So he still thought about very small particles that we can't see with naked eye, but they are charges. And the assumption was, which is true, there's only a certain number of charges at a given time associated with an object. And these charges may jump from one object to another. So when you rub the glass against silk, that's what actually you're doing. You know, charges are going from one object to the other. Same thing with the plastic and the fur. Now, in our modern understanding, the thing that jumps is the electron, okay? The positive charge, the proton, will never charge from one object, will never jump from one object to another. It will be the electron. So in order to create an object, or in order to charge an object with a positive charge, in the case of glass, for instance, you have to take away electrons from it. Remember, initially there were equal number of electrons and protons. There were equal number of negative and positive charges, but by rubbing the glass against silk, you took some of the electrons from the glass and transferred them to the silk. So you are left with an excess number of protons, or positive charges, on the glass. That's what makes it a positively charged object. In the case of a plastic, though, you're actually taking the electrons from the fur. The electrons jump. Okay, so like these red dots here will be electrons that will jump over to the plastic, and it's going to make it negatively charged. In the case of the glass, you will have the electrons, okay, there's some yellow, jumping to silk and leaving this positively charged. Okay, so that's the modern understanding of why we have charged objects. Okay, same thing happens with clouds during a storm. those clouds will be charged, and then when the when the charged clouds discharge, you know, when those charges, electrons, have a way to go from either from one cloud to another, or from cloud to Earth, or vice versa, sometimes from Earth to cloud. That's what we see as, you know, lightning and thunder and all that. Okay, so electromagnetism is a fundamental force. It's an interaction. Now, when I say fundamental force, I'm not talking about forces which you're familiar with from physics 1. Like you push an object, you pull an object, or you hang an object with a string and there's a tension in the string, or there's a normal force, okay? I'm not talking about such forces. I'm talking about something deeper than that. In principle, all contact forces can be reduced to electromagnetism, okay? There's an object here, a phone cover, and I'm pushing from above. Yeah, there's contact there, right? But what is the force? What is the fundamental interaction that keeps the pen from going through the object, right? If you think it like that, it's not something you can find out easily. You have to think about the material, right? I mean, the material is made of atoms, molecules, and how are these molecules staying together as a solid object? That's electromagnetism, right? I mean, the force that keeps the proton and electron together is the same force that keeps molecules, you know. I'm not sure what this is made of, some polymer or some plastic, but these are all put together, stay in place because of the electromagnetic interaction between molecules. So it is actually electromagnetism that keeps my finger from going through the object. All right? That's what makes it a fundamental interaction. It acts at a distance. You don't have to have a contact, physical contact between the two forces. Just like gravity, right? When Earth pulls the moon, there's this interaction between the two objects, although there's a lot of distance between them. You don't have to have physical contact. These are associated with what we call fields. Field. A field is a very effective way to describe a force, basically. Like electric force, electric field. Gravitational force, gravitational field. Okay, these are vector fields. Vectors are objects with direction and a magnitude, all right? A number and a direction with it. So if you fill your space with numbers, you obtain a scalar field, like the temperature variation in this room, okay? For every point in this 3D space, you may have a number, and that number would represent the temperature in this room, for instance. But what if you add a direction to each number? This could be a flow, like airflow, okay? You could, if you open the windows, right, there's air coming in, and then the molecules start moving, air molecules, and you can think about the velocity of those molecules. That's speed and direction, right? It's a vector. So a scalar field now becomes a vector field, all right? So in the case of gravity, you would have the object, let's say the Earth right here, and around the Earth, you will have these vectors, specifically, you know, pointing to the Earth, because we want to get an attractive force, remember? And the closer you are to the Earth, greater the magnitude of these vectors. And if you're far away, you have smaller vectors, shorter. Okay, so imagine these vectors fill up the entire space around the Earth. And what do? Now you place another object, a second object here, let's say our moon. You place the moon right here. Now, one way of looking at this problem is just applying, Newton's universal law of gravity, which is, the famous formula. Maybe you remember from Physics 1. This force is given by this universal gravitational constant times mass of the Earth times mass of the moon divided by the square of the distance between them, right? That's fine. But if you want to think about why we have this force in the first place, I mean, how can Earth affect the moon, which is over there, So to get around it, you introduce this concept of vector field that I just described. And that's actually due to Faraday, Michael Faraday. So if you do that, you just worry about the interaction between the moon and that vector where the moon is, okay? You don't have to worry about everywhere. It's a local interaction between the moon and that specific vector, special vector. And then you can think of the force as the mass of the moon times the field, gravitational field at that point, okay? So that's a really good way of looking at forces through this idea of a field. So when I say a fundamental force of nature, I'm talking about forces which have to do with these fundamental fields, also called fundamental interactions. Turns out there are only 4 of these, okay? We don't know a 5th force. Number 1, gravity. That's gravity. Number 1. Number 2, it's electromagnetism. Okay, the force between negative and positive charges, protons and electrons, and also magnets. Turns out there are 2 more forces like these. These are called nuclear forces. So the nucleus is made of protons, right? Now, according to this logic, 2 protons should repel each other because they're both positive charges, but they stick together. Like look at a helium atom, which has 2 protons and its nucleus, and they stick together. Why? They should be repelling, right? This means that there must be a force stronger than the electric force. Okay, the electric force tries to separate the protons, but this force keeps them together, all right? That's why we call it the strong nuclear force. Strong nuclear force. It not only keeps the protons together, also neutrons. Like in a helium atom, we have 2 protons and then 2 neutrons. These particles weigh almost the same as protons, but they don't have any charge, okay? So there is no electromagnetic interaction between 2 neutrons or between a neutron and a proton, but they still stick together. Why? Because of this strong nuclear force that keeps them together. So it's strong, much stronger than electromagnetism, definitely stronger than gravity. Gravity is the weakest force of all. So what are the differences between electromagnetism and the nuclear forces? Well, electromagnetism acts from 0 to infinity, okay? There's no limit for its range. But the strong nuclear force is only effective within small distances. Like 2 protons, if you separate them, 1 centimeter apart, they will definitely repel each other and there will be no strong interaction between the 2. It's only when you push them really close to each other, okay? The distance between them is so small, in that realm, in that small distance, this force kicks in, and then they start attracting each other instead of repelling. All right, so that's strong nuclear force. And if you're wondering, where does it come from, right? Then you have to dig into the structure of protons. Protons are not the smallest particles, okay? Just like an atom is made of protons, neutrons, and electrons, both neutrons and protons are also made of smaller particles, which we call quarks. So these particles, we have 3 of them, 1, 2, 3. These are called quarks. When 3 of them are together, we call it a proton or a neutron, depending on what kind of quarks we're using, okay? Very strange particles. And it's as if these are connected with springs. Okay, a spring like this. Not real springs, but the idea is they're just like a spring. The force that keeps these quarks together acts like a spring, because when you try to separate them, the force increases, okay? Unlike magnets or gravity, like if you increase the distance between Earth and the moon, what happens to the force? It goes down, right? This doesn't happen to quarks. Try to take them apart, the force between them also goes up. So when you have another, let's say, proton here with the 3 quarks and then those springs, okay? Now these 2 quarks also interact, all right? So the strong nuclear force is actually nothing but the force that keeps the quarks together. It keeps proton as a whole, and also it makes a proton attract another proton through this mechanism, which I try to explain using springs. It's more complicated than that, okay? It's just a simplification, but that's the idea. And the 4th elementary force is called weak nuclear force. The weak force. What happens is these neutrons and protons transform, okay? A neutron can become a proton. And during the process, it releases some other particles, which we detect as radiation, okay? So the weak nuclear force is responsible for radioactivity, radiation, right? So much about fundamental interactions. There are only 4 of these. So we're gonna be focusing on, in this class, is the second one, which is electromagnetism, all right? And for a couple of chapters, we're just gonna work on electro part of it. And then in the second half of this class, we're gonna move to magnetism, okay? But keep in mind, Max will show that they're one and the same, okay? Electricity and magnetism are actually the same, 2 sides of a coin. And it was Albert Einstein who actually showed that electromagnetism, actually, if you try to reconcile electromagnetism with Newtonian mechanics, you go into some trouble, all right? It was Albert Einstein who fixed that problem, basically. Anyways, so let's start from this force between charges, which we call the electrostatic force or Coulomb force. Let's start there and see how this goes. By the way, in order to charge an object, this is not the only way, like glass against silk or plastic against fur. So these objects are not conductors of electricity, okay? So we have 2 kinds of materials. They're either conducting materials or insulators, or non-conducting, let's say. And this has to do with the material, whether it has some free electrons or not. So in a metal, okay, let's say copper. In copper, you will have these nuclei, protons, positive charges, and electrons, many, okay? So most of the time, these electrons will be around the nucleus. But in the outer shells, you will have 1 or 2 electrons, which are actually free to go from one atom to another. They travel, okay? These are called free electrons. So most metals have this property. And if you try to conduct electricity through this object, you're going to be successful because these free electrons will provide the charge flow, okay? But in an object like a plastic, you don't have that, all right? You don't have these free electrons. They can't move around. So as a general principle, materials that conduct electricity are also, good conductors of heat. There are exceptions, okay? But as a general principle, that works. So a metal could be a good heat conductor and electricity conductor. Then how would you charge a conductor? Let's say you have a sphere, a metal sphere. Okay, so initially there is no charge here, right? Let's say this is a conducting metal sphere. Initially neutral, there is no charge on it, and it's sitting on a pedestal which is made of wood, which is not a conductor. Okay, so how can you charge this? So there's this method of induction. That's how you charge them. So basically, you remember those glass sticks? The glass, let's say the glass had positive charges, right? It had lost its electrons to the silk. Now, if you bring this glass near the conducting middle sphere, what's going to happen? The conducting sphere has free electrons, remember? Those electrons will feel the presence of the positively charged glass, so they're going to move towards the glass. So the negative charges will move to this side of the sphere. Why? Because opposite charges attract. Remember, the negative charges, the electrons, will be attracted by the glass tube. They're going to move there. Now, just because negative charges move to one side, the other side will automatically become positively charged. Okay? Not because positive charges moved, the protons can't move. Remember, the protons are fixed. There's a structure to the object material, like a crystal, right? It's the electrons that move, but the absence of electrons on that side makes that side positively charged. All right? So, have we charged the sphere? No, because the total number of charges are equal, okay? They're equal number of positive and negative. All we did was to move the negative charges from one side to another. Like if you take the glass and move it, take it out of the picture, those negative charges will go back to their original places or whatever. They're going to be distributed around the sphere, and the total charge will still be zero, neutral. But at this point, while the glass is still close to the sphere, we can do this. We can take a piece of copper cable, okay, a piece of wire, and then attach it to the sphere on the other side where we have positive charges. And you can take that and then, well, you can just ground it, you know, ground. You know, dig a hole in the ground and then stick it in the ground. Ground is a reservoir of infinitely many charges. So what happens is, since it's a wire, a conductor, a copper wire, let's say copper wire, you're going to borrow some electrons from the ground, from Earth, all right? So those electrons, let's use green, will travel. Okay, how many electrons? Well, depends on how much you need. This is the excess charge here. These are the positive charges. These positive charges will attract those electrons, and that many electrons will go and then neutralize here. Okay, these will be now positive, negative, positive, negative, positive, negative. You have equal number of positive and negative charges on that side. All right, but the other side is still negative because that's near the glass, which was positively charged. Now at this stage, if you take the glass out of the picture, same thing will happen, meaning those extra electrons would go back to Earth, okay? Now we don't want that. We want to charge the sphere. So what do? We cut the wire, okay? You cut the wire from here while the glass is still near the sphere. You cut the wire and then move the glass away. So those electrons that you borrowed from the Earth cannot go back to Earth. They remain on the sphere. So now you have a negatively charged sphere. Okay? So once you have more electrons than you have protons on that metal, it is negatively charged. And you take the glass away. Now those negative charges, electrons will push each other away. So they will be equally, uniformly distributed over the surface of the sphere, okay? That's called induction, charging by induction. That's how you charge conductors. One more thing I wanted to say. What about insulators like paper, okay? Paper clippings. You take that plastic, you rub it against fur. Now you have, let's say, an object which is negatively charged. This is plastic. And now we have little pieces of paper here. You bring the plastic close to the paper, and then suddenly they're attracted to the plastic. Why is that? Is it because that pieces of paper, were they positively charged? No, they don't have to be charged. They could be still neutral and still attracted. And here's why. So if you zoom in on this paper piece here, okay, so what you see is something which is made of electrons and protons and all that, right? And remember, it's an insulator, so electrons are not free to move from one side to another, okay? They can only move within a very small distance. Well, what happens is, and this is true for pretty much all kinds of insulators, no matter what kind of material it is, what happens is, within that small scale, you can still push things around. So imagine you have this atom here, or a molecule, which is neutral, okay, equal number of positive and negative charges. But just because you have a negatively charged plastic close to the paper, the side of that domain, when I say domain, I mean very small part of that object, you know, that molecule, whatever that is. It's going to orient itself such that the positive side faces the negatively charged plastic, automatically the other side will be negative, or vice versa. Okay, so if you think about all these domains here, they will be all lined up like a compass in a magnetic field. Okay, but this is for electricity. So these sides will be positive, negative, positive, negative, positive, negative, positive, negative. Now we have many of those, and of course, when you have two objects side by like these two, let's say you have negative here and positive there. So this part is still neutral, but you are left with some excess positive charge on that side. Similarly, on that side, you will have negative charge. All right? So that's why this piece would be attracted to the plastic. It's not really charged, but within the objects, those little domains orient themselves so that you have a positive charge on the side of the object that faces the negatively charged object. All right, same thing happens when you use a comb with your hair. It's going to attract your hair. On a dry day, you know, you get out of your car and the door shocks you, you know. Anyways, okay, so that's so much about the electric charge. I mean, you can read more about it in the book. Let's talk about Coulomb force. All right, so let's say you have two charges. I'm going to call them Q1 and Q2, okay? These could be positive, 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 negative, negative, positive, or negative, negative. Doesn't matter, okay? Any two charge, which are separated by a distance r. Okay, this just looks like gravity, all right? It looks like gravity, if you remember that from Physics 1. So the force between them, all right, F, and this is called the Coulomb force, or Coulomb's law. Okay, so this force could be repelling or attracting, okay, attractive or repulsive. This force will be proportional to the charges, so Q1 times Q2. And according to Newton's third law, action-reaction, the force on the first charge, call it F12, will be the same in magnitude, same as F21, and that is the effect of charge 1 on charge 2, right? But they have opposite direction, so F12 is equal to negative F21. Now, this force doesn't change its magnitude when you swap the charges. So multiplication works just fine because the order doesn't change anything in a multiplication. But when you separate the distance, when you separate the charges so that the distance increases, let's say, the force decreases, all right? So there has to be an inverse relationship between the force and the distance. Now the candidates are r squared, r cubed, okay? You won't have something like 2.3. That doesn't really happen in nature. You're talking about integers here, but which one is the correct one? Is it 1 over r squared, 1 over r cubed? Well, that's when you do have more theory and experiment, you know, just like you had the Cavendish experiment in the case of gravity. You could do it actually even easier because electromagnetism is a strong force compared to gravity. You can just use a torsion balance and measure the force between the two charges and the distance between them and all that. Turns out, long story short, it's r squared. So it's an inverse square law. Charges are measured in terms of coulombs. So that's the unit for electric charge, okay, named after Coulomb, C. R, of course, in meters, right? So we have Coulomb squared per meter squared, but we have to end up with newtons here, right? Newtons, and what is a newton? 1 newton is 1 kilogram meter per second square, right? Do you see any seconds on the right hand side? No. Do you see any kilograms? No, right? I mean, kilograms, meters, and seconds, they're fundamental units. We also have derived units. Newton is a derived unit. Turns out Coulomb is also a derived unit, if I'm not mistaken. So we need a constant here, okay? A proportionality constant right here. Okay? That's why it's, I said this looks like a Newtonian gravity, right? Instead of the capital G, which would be the universal gravitational constant. Now we have this constant, which will have units of, so let's see, we need newtons here, right? So newtons times meter squared per Coulomb squared. Oops, not O, Coulomb squared. That would be the unit of this constant, okay? It's an electrical constant, or Coulomb's constant, okay, is approximately equal to 9 times 10 to the power 9 newtons meter squared per Coulomb squared. Okay, that's a numerical value, a great number, large number. Remember, in the case of gravity, G was 6.67 times 10 to the negative 11, right? That was Newton meter squared per kilogram squared. That's much greater. K. Now this K is also written as 1 over 4 pi epsilon 0. Okay. So, well, why 4 pi? I mean, this is going to be clear, not today, but when we do Gauss's law and all that. So epsilon 0 is called the electric constant. Electric constant, or permittivity of free space. Permittivity of free space. Okay, you can do the math. I mean, you can multiply this by 4 pi and then take the inverse. So that is 8.85 times 10 to the negative 12, I believe. You can do the math, okay? Just multiply K by 4 pi and take that number and find the inverse of that number. So this is going to be Coulomb squared per Newton meter squared. All right. So that is the alternative way of describing this constant. I'm going to use it a lot, okay? 1 over 4 pi epsilon 0. That's the Greek letter epsilon. Epsilon. Okay, epsilon 0 means that's free space. If you're inside a material, that's a different number. We're going to come to that later. Okay, so that's the form of this force. F equals that constant times the charges times R. So this could be repulsive or attractive. So just to make it just the magnitude, I'm going to put 2 bars next to the charges. So I'm talking about a positive number here, okay? It's a positive number. Of course, if I want to use vectors, I want to use directions, I can use unit vectors. You can do it any way you like. Like you can take your x, y axis here, x, y, You can put a positive charge here, and then you can put a negative charge. Okay, so you can find the force on this negative charge, and you can express it in terms of your unit vectors. Remember unit vectors, I hat and j hat. So these are the, I'm gonna put it here, small vectors of unit length in the x and y directions. So you can express this force in terms of I hat and j hat. Actually, let me just solve a problem like this so you'll know what I'm talking about. So x, y, let this be Q1, which is, how about an electron, okay? An electron charge is the smallest charge you can think of, okay? It's a unit charge. In a way, you quantize the charges, you divide them into small pieces, and then you can't divide into a smaller charge anymore, except for quarks, a different story. Remember the 3 quarks in the proton? Those are fractional charges, but the unit charge is an electron. And let this be an electron. So that's 1.6, negative 1.6 times 10 to the negative 19 coulombs, okay? So 1 coulomb is a huge charge, okay? We have a 10 to the negative 19 here for an electron. And then I'm going to place a positive charge here. Let's say a proton, okay? Right here. A proton has the same charge. It's much heavier than an electron, but it has the same electric charge. 1.6 times 10 to the negative 19 coulombs. So I know that these will be attracted to each other. So the force on the, let's find the force on the electron first, okay? I'm going to imagine the line that connects the 2 charges, and I'm going to say there's now a force on the electron pointing to the proton, right? That's an electron, it's a proton. So where is the proton? The proton is x, let's say, I don't know, 4 meters. X and y are meters. And the y coordinate is what? 3. 3 meters. Okay, so let's just write the force as a vector using unit vectors. And let's calculate the magnitude as well, all right? So this force on the electron will have an x component and a y component, right? Now, if this angle here is theta, the x component will be f cosine theta, right? Times I hat. And the y component would be f sine theta. And then I multiply it by j hat. But what is f? So f will be that constant, 9 times 10 to the 9, times these charges. I have 2 of them, so I'm going to square it. 1.6 times 10 to the negative 19 coulomb. Just square it, okay? And I'm just finding the magnitude, remember? So it's a positive number now. So I need the square here, 3, 4, 5, right? This is 5 meters. 5 squared is 25, or 5 squared. All right, so let's find it. Uh, 9, 10 to the 9 times 1.6, 10 to the negative 19 squared divided by 25. So this is 9.2 times 10 to the negative 30. Look how small it is. Newtons. All right. I'm just going to plug that in right there. Of course, I need the cosine and sine now, right? So cosine will be 4 over 5, and sine will be 3 over 5. Okay, do I need to finish this? Let's finish it. So times 4 divided by 5. 7.37 times 10 to the negative 30 newtons in the x direction. And then whatever you get by multiplying this number by 3/5 and then add a j hat there. Okay, that's the force. You can do the same thing for the proton. I mean, find the force on the proton. It'll be the same force, only in the opposite direction. So just put a negative sign in the front, okay? That's all you have to do. Very simple problem, very simple. There are more examples in the book. Like you can think of those charges like billiard balls on a pool table. Okay, you can put them in any configuration you like. You know, you can take those charges, place one here, place one over there, and the one over here, and then now you have 3 charges, so you have to consider 2 forces on a single particle, right? And you can add those 2 vectors, just like adding 2 vectors. You can find the net force. So I'll leave that to you. Let's move on to something else, okay? That's the Coulomb force. Let's remember the Coulomb force is 1 over 4 pi epsilon 0, which is this constant here, times Q1 times Q2 divided by the square of the distance between the 2 charges. What if you don't have 2 charges or 3, but many, many charges, okay? Like the glass rod you charged in the beginning. Now, it's not a point anymore, but like a cylinder, okay? A finite size object. So how do you find the forces due to such charge distributions? To do that, maybe now it's a good time to introduce the field concept, all right? So here's what you do. If you go back to the elementary concept of the Coulomb force, when you have 2 charges, Q1 and Q2, there's this force between them, right? Now, imagine you remove Q2, okay? You only have Q1. But Q1 creates this field around it, just like the Earth and the Moon example. Earth created the field and the Moon was in that field. Same idea, okay? So the first charge will create a field around it. And the rule is if it's a positive charge, the vectors that make up that field would be radially outward. Okay, so imagine arrows going away from, pointing away from the charge in all directions. Think in 3D, okay? In all directions, you have this. And as you move away from the source charge, the magnitudes will get smaller. So right here, you have a small arrow. Over here, even smaller, okay? So where Q2 is, you have a smaller arrow, but still there, okay? Now, if you put the Q2, the second charge, to that location, which is R away from the source, now we can think of an interaction between the charge Q2 and the field only, okay? And it's very simple. If you just remember the formula, Coulomb force, you had K, Q1, Q2 divided by R2. Basically, you take this part, K times Q1 over R2, and give it a new name, okay, called the electric field. Letter E stands for electric field. Electric field, and E times that charge gives you the force on that charge, okay? So force will be equal to the charge times the electric field. But the value of the electric field at that point where the charge is, okay? This Q is the charge that you want to find the force on. The electric field is due to the source charge. That was Q1. This is Q2, if you will, okay? I didn't put the index 2 there, but you know what I'm talking about. You have a source that creates the field around it. Now, once you get this idea, you can forget about the source. It's only the field you have in space. The field is everywhere. And then you place your second charge, call it a test charge, if you will, okay? And place that charge somewhere in that field. The charge will interact with the field where it is placed. That's what Q times E is, okay? E is the electric field, Q is the charge. If you multiply the two, you get the force on that charge. So if this is your charge, and if there's a field here, which I'm going to show by these arrows now, okay? So it's a vector equation. F as a vector is equal to Q times E. If Q is positive, then it is just a positive scalar, right? Which means F and E are parallel. In that case, the force on Q would be also in the same direction. But if Q is negative, let's say negative 1 Coulomb. What do you have then? F is equal to negative 1 Coulomb times the electric field, whatever it is. But now electric field points this way, the force points in the opposite direction. Okay, so for a negative charge, this was positive, but if you place a negative charge, the force will be pointing in the opposite direction of the electric field. All right? So this is electric field. All right? So for a positive charge, now instead of using separate arrows like this, I'm just going to continuously draw a line radially outward like this and put an arrow on it. This will be my electric field, if that's a positive charge. Okay, I mean, instead of putting an arrow here, another arrow here, another arrow, and the arrows get smaller and smaller because it's 1 over r squared, all right? Instead of drawing it like this, I just draw a straight line. But I know that if I move along that straight line, the strength of the field will go down. I know that because I'm moving away from the charge. Now, if I have a negative charge, let's put the negative charge here. Same idea. I'm going to draw lines radial, okay? But they're going to point to the charge, radially inward. Okay, so a negatively charged charge, a negative charge, will create a field around as well. But the direction of the field is to the charge. If it is positive, it's moving away from the charge. If it's negative, it's going into the charge. So what happens if I put the positive and negative together? Something like, let's say, I have the negative charge over here. I have the positive charge. And they're separated by 10 centimeters, okay? So I know that the field has to go from, it has to go radially outward from the positive, but then it has to go radially inward toward the negative. So that's what I will have, okay? That will be electric field. Here, this line will go normally outward. Here I will have a negative, oops. Okay, here's actually, maybe we need to analyze this a little bit better. Let me not go too fast. Now, remember those arrows? So imagine a point here, right there. Now, think of the charges separately. Because of the negative charge, I will have a vector that points this way. But because of the positive charge, I will have a vector that points this way. Why? Because it has to be radially outward. Imagine this point right here. Now, if I imagine a line that joins that point with the positive charge, I will need a field due to the positive charge that points this way, but due to the negative charge, okay, my lines are not straight. Sorry about that. Try it again. Oops. Okay, not very good, but you know the idea. Right here, though, you will have a field that points to the negative charge, radially inward, remember? But I cannot have two separate vectors, okay? What I have is one field. See, the thing about electric field is you can always add them up, okay? Like a superposition principle, if you will. So what I should really be doing is, just adding these two vectors. So if you add them using the graphical method, from vectors, gives you something like this, right? Oops, my lines are really bad today, okay. Similarly, over here, you have two vectors. Draw your parallelogram and end up with that, okay? So, if you consider the contributions of such points all around the two objects, you will end up with lines. Now, let me go back to red. That's the color I started with. You're going to end up with lines such as these. All right. Now, the direction of the field is like this, from positive to negative. I mean, even these ones should go from the positive to the negative, okay? And you may have endless possibilities, okay? You don't have to have point charges. You have a line as a charge, a distribution. So what if you had something like this? Let's see. Can I move this? Yeah. What if you had a line of charge? Let's see, these are negative charges. And then you have a positive charge here. And how are you going to draw it? Yes, it has to go from positive to negative, and then in the middle, you will have simple a line like this. But what about this one here? Now, it's going to curve and hit the line charge like this. The rule is, by the time you reach the negatively charged line, you're away from the positive, and those lines have to be sort of perpendicular. Okay, I mean, of course, it depends on how long the charge stick is, but this is the general idea here. Okay, but of course, if you're close to the edge, you know, they're gonna be curved as well, like this. Okay, something like that. Of course, you will have other field lines here as well, negative. Well, this side, well, it depends how it is constructed, whether it's a conductor or not. But like I said, the possibilities are endless. Okay, so that's what we're going to do from now on. Okay, we're going to calculate the electric field given a specific charge distribution. That's our goal from now on, how to find the electric field given a charge distribution. So let's describe this formula for the electric field in a better mathematical form first. So I'm going to use, we live in a 3D space, right? Three-dimensional. I'm going to use the three coordinate axes, x, y, z. Let's think about the most generic thing. So let's place our source in the origin. This is the source for the electric field. Question, what will be the electric field at a point here? All right. Now I know it's going to be radially outward, yes, but how do I express it with the formula I have? So this is the position vector, if you will, R. So what is the electric field at R? As a vector. As a vector, of course, it points radially outward. I know that. So that is the direction of E. Okay? I mean, I'm not going to introduce spherical coordinates or anything like this. Maybe I'll do later, the next chapter or something. You can still use I, J, K, no problem. You know, I mean, that's I hat, J hat, and K hat. Or you can just stick with the R, right? R is your position vector. Position vector. Now, in this case, the direction of E is the direction of the position vector, right? That's what radially outward means. So E is radially outward. So we'll need the unit vector, R hat, just like I hat, J hat, and K hat, with unit length. We'll need an R hat, which is also unit length. And you define it as the position vector divided by its magnitude. Okay, so using R hat, now you can write the electric field as your constant 1 over 4 pi epsilon 0 Q divided by this squared times R hat, all right? Or if you will, 1 over 4 pi epsilon 0 Q over, now we can make this R cubed, and you can add an R here. Same thing, okay, just using the definition of R hat. Okay, the force is still 1 over square type of inverse square type of force. I'm just changing the way I write it. But that's the general form for a point charge. But what if the source is not a point? I mean, your X, Y, Z are still here, but the object you're considering is some weird object, okay, with a lot of charge, and you still want to find the electric field here. How? Right? The charge is everywhere. So this R is the vector from the origin, but the charges around the origin, you know, there's a distribution. So how are you going to find the electric field? Because remember, the additive property of electric field, the superposition. So for instance, you have a contribution from this corner of the object, which contains some charge. Then you have to consider this distance here from that charge to observation point. And then you have another charge over there, which is this much away from your observation point. Okay, so you have to, which R is the R that you're going to use in the formula, right? In the formula, you only have this R here, which is from the origin. So this problem cannot be simply solved by taking this formula and then changing a variable. You can't do it. You have to use calculus, all right? You have to add the contribution from each infinitesimal charge that makes up the whole charge. You have to sum over those charges. In other words, you have to integrate. So that's what I'm going to show you now, how to do this integration. Let's take a short break. Let me pause the recording. I'll be back in 5 minutes. All right, so charge distributions. This looks kind of arbitrary. Let's start with a uniform charge distribution. Maybe the simplest shape you can imagine, like that plastic rod you are rubbing against fur, right? Let's take something like that. So let's say uniform charge distributions. Electric field due to a uniform charge distribution. You see, if you find the electric field, finding the force is very easy. Just multiply the field at that point by the test charge, that's all. So it all comes down to calculating the electric field, all right? So keep in mind that electric field is a vector. That'll be important. So I said a charged rod, right? So let's draw it. You know, here's like a cylindrical object which carries some charge. All right, let's say positively charged. This was maybe a glass tube. You rub it with silk, and now it is positively charged. And you want to find the electric field right here. Let's use blue. Right in the middle, let's say, you move to a point here, which is A away from the rod, okay? So I guess you can guess that it's somehow pointing to the right. Just because we have positive charges as our sources, and each positive charge, there are maybe a million, billion little charges that make up the whole thing, right? But each charge will create a field radially outward from it, and there's no reason why at a point A away from the source, you should have a point, you should have a field that points to the charge. It's the other way. So it's going to be somehow to the right, but how exactly? You have to think about it. And let's say the dimensions of the rod is given by this parameter L. If the length is L, all right, and half of it is above and half of it is below. So let's say this is L over 2, and this will be L over 2 as well, okay? So let's use some coordinates here. Let this be the x coordinate. Not that it really matters, because this coordinate is kind of, I mean, once we can find the electric field at point A, we could replace A with X, and then now we have a formula for electric field along that line. You may think like that too, right? So for future, maybe you may need X, but for now, it's not that important, but the vertical is important. So let's call this Y. So I'm going to call this coordinate here Y, okay? So this point is Y equals L over 2, and this point here becomes, of course, negative L over 2. Anyways, okay, so I have the formula that gives me the electric field for a point charge, but now I want to find electric field due to the charge distribution. So how do I do that? Well, I got to use the things that I already know, all right, which is the field due to a point charge. So why don't I consider the smallest charge I can think of along that rod? Okay, so somewhere here, let's say, imagine a small, really small portion here, maybe another cylinder, but really small. It's such small that its thickness is differential or infinitesimal. Now, the thickness of that green area or volume is just dy. How about that? dy, very small. D stands for infinitesimal or differential, right? And that carries a charge dq on it. dq, okay? Very small. Now, the rod itself may carry a total charge of q, and this q is evenly spread along the line, right? But I'm talking about only dq right now. And because of that dq, I will have an electric field at this point here. Now, to find the direction of the field only due to dq as a source, I have to combine this point and the observation right there. And therefore, the electric field would be radially outward. Remember, that was the rule. So this is my electric field. Just because of dq, and I can call it dE. Okay, but there are many such dqs along the line, so you have to consider them as well at one point, right? So this is not the result. It's only due to that little source, dq. But now I'm allowed to write dE, at least the magnitude of it, using that formula I have, right? 1 over 4 pi epsilon 0. In the denominator, I will need r squared. This is r from here to the observation point. R squared, okay? Not to be confused with the r in the previous picture. That was the position vector. I mean, if you're uncomfortable with the letter r, you can use something else, doesn't matter. I just called it r. In the numerator, I will have the source charge, which is just dq. All right, so that's dE. Now, what is r? R is, okay, we have a triangle here, a right triangle. This side is A, and along this direction, since this is where y is 0, actually, this point is y away from that origin. So this side is y, right? The vertical side of the triangle is equal to y. Then using the Pythagorean theorem, this is square root of y squared plus a squared. All right? Good. So we got rid of r anyways. I didn't need the variable r anyways. We got rid of that. It's just y. Y will be our variable. A is a constant, right? Y is the thing that changes. So y changes between negative L over 2 and positive L over 2. Okay. What about dq? What is dq? Now, this is a uniform distribution. Uniform. Which means that the dq over here will not be different from dq over there as long as the thickness is still dy, right? Or over here, for that matter. Doesn't matter where you are. If your infinitesimal charge is independent of your position variable, which is y, we call it a uniform charge distribution. Does it have to be that way all the time? No, it doesn't have to be. It could be coordinate dependent, and it wouldn't be uniform anymore, all right? But if it is uniform, then we call it a uniform density, okay? So density. Density, it tells you how much charge you have in that small volume. Now, the letter, there are many options here. Usually, people use lambda for linear density, L lambda, right? Lambda. Lambda. Sigma for area, the charge distributed over a rectangular plate, okay? The density would be sigma, just notation, all right? And a volume, that would be rho. Okay, just letters, common letters, which are used for density. You can use your own letter if you like, I don't care, right? But since it's a linear distribution now, see, I'm considering a very narrow cylinder, right? I'm just not worried about the thickness of the cylinder. So linear density is enough. Linear. This is linear. This is for area. This is for volume. Just a general, notation, convention. So if it is a uniform charge distribution, lambda is simply the total charge divided by total length. Q over L, okay? If this was Q over L times Y, it wouldn't be uniform anymore, or Y squared, or sine Y. A function of Y would be enough to make this non-uniform. But in this case, there's no coordinate in it, so it is a uniform charge distribution. Simply total charge divided by total length. I mean, this is very similar to mass density, right? You take the mass of an object and divide it by its volume, you get volume mass density. Same idea. This is charge density. Linear charge density. Then dq, which is the charge contained in that small volume, or in this case, length, I should say, in that small length, will be simply lambda times dy, because length is dy. Okay, I mean, it's so easy to check this. I mean, if you integrate this, for instance, the integral of dq, which is the integral of lambda dy. dq, if you integrate it, which means add every little charge, you're going to end up with total charge. This is q, total charge. And here you will have, let's do the integral. So you have lambda, which is q over L times dy, but y changes from negative L over 2 to positive L over 2. So if you evaluate this integral, so q and L are constants, you have integral of 1, which gives you y from negative L over 2 to positive L over 2. That gives you Q over L times L, which is Q. That's what you expected, right? Okay, so that's the idea. That's how you find dq. So all you have to do now, take that dq and plug it in the expression for dE. But you got to be very careful here. That expression here is only the magnitude. But what we want to find in the end is the vector, the electric field as a vector, which means we have to consider the components. Like this one here, draw a box around it, usual method, right? So recognize, recognize the vertical and horizontal sides of that box as the components. All right, so this is DEY and this is DEX, if you will. Now, what happens is, no matter where you are along that rod, you will have these two components, maybe except for where y is equal to 0, then you have only x component. But in general, you have both y and x components. Whenever you're above y equals 0, DEY points downward, and whenever you're in the lower part of the rod, the corresponding DEY points up. And because of the symmetry, you know, we have equal parts and uniform mass distribution, uniform charge distribution, those vertical components, when you add them up, will cancel each other. Okay? So in the end, if you add the contributions from each little charge here, those vertical components will cancel. But the x component will never cancel. All right? They will not cancel. And remember, this is true because of the symmetry. If I were calculating electric field on a horizontal line above y equals 0, I wouldn't have that symmetry. There would be more up-pointing y components than down-pointing components. So that's only for this problem. I can use that symmetry, which means I can get rid of the y component, and in the end, what I will have here will be only the x component. Okay, the net field will be pointing in the positive x direction, which means that I have to use the component instead of dE itself. So this angle here, call it theta, which is also here, theta. If you consider the cosine of that angle, cosine theta, that's what I need to multiply the hypotenuse with. Hypotenuse is dE, right? So this expression here has to be multiplied by a cosine theta factor. So let's do it. And while we're doing that, we're gonna plug in dq as well. So we have here 1 over 4 pi epsilon 0, our constant. Remember, 9 times 10 to the 9, that constant. That times dq. Now, instead of dq, I'm gonna write okay, I can either write Q over L or I can use lambda, doesn't matter. For now, let's just write Q over L. So Q over L times dy. Okay, so lambda is Q over L, lambda times dy, divided by r squared, which is y squared plus a squared. All right, that is the square of r, but I need to multiply this by cosine theta. So here's the cosine theta, a over r. So a from the right triangle here, a divided by r. R is square root of y squared plus a squared. All right, so this is equal to Q times A divided by 4 pi epsilon 0 over L times L. Dy divided by y squared plus a squared. All right, now I guess you know what's going to happen now, right? We're going to integrate this. We're going to integrate this. So these are just constants. Dy varies between negative L over 2 and positive L over 2. Okay, I forgot to add this here. Y squared plus a squared. There's 1 and 1/2, so 3/2. Okay, our integrand is 1 over y squared plus a squared to the power 3/2. Now, you can look up this integral in a table. That's fine. I don't care how you do it. It's just calculus. Or you can use the methods you already know for integration. Actually, when you're doing this, maybe it's even better if you just use theta as your variable, because you're going to do some trigonometric substitution anyways, right? So at this point here, I mean, instead of converting everything to y, you could make this substitution here. Let's say you could say y, look at the angle here, theta, right? You have, let me scroll this up here. You have y divided by a equal to tangent theta, right? Tangent theta, which is equal to sine over cosine. Sine theta over cosine theta. So this means that dy would be a times, I'll take the derivative of the right-hand side, sine's derivative is cosine, cosine times cosine, cosine squared theta minus sine times derivative of cosine, which is negative sine. So I make this plus and sine squared theta, and divide by the square of the denominator, cosine squared theta d theta, right? And the numerator is equal to 1, right? So dy would be equal to a d theta over cosine squared theta. Now you could take this and instead of working with y, you can just work with theta, right? So here you have q over 4 pi epsilon 0 L. Now dy is this, a d theta over cosine squared theta. Now you will need here what is that? Y squared plus a squared. So y squared plus a squared is a squared tangent squared theta plus a squared, which is a squared. Tangent squared is sine squared over cosine squared. Sine squared theta over cosine squared theta plus 1, factoring a squared out. And then here you have sine squared plus cosine squared in the numerator, which is 1 again. So you will have a squared divided by cosine squared theta, right? And then you flip it, so you get cosine squared theta over a squared. That's just from here. And then you have here a, okay, another a divided by square root of that, which is a over cosine theta. So let's see what cancels out now. So this a takes care of that a. This takes care of the square here, 1a left. Cosine squared, only cosine theta left. All right? So you're integrating Q over 4 pi epsilon L. Where's A? A is here. 1 over A. Integral of cosine theta d theta. What is the integral of cosine? Sine. All right, so this integral will give you Q over 4 pi epsilon 0 LA sine theta. Okay, limits. Now, lower limit and upper limit. Now, those limits were in terms of y, negative L over 2 and positive L over 2. It's okay. We can just write them in terms of theta, right? So below, so let's say lower limit, higher limit. So you have here theta L over 2, negative L over 2. This is A, right? So sine is this divided by that. So we're talking about high limit is L over 2 divided by A. I'm sorry, not A. That would be tangent, right? L over 2 divided by square root A squared plus L over 2 squared. Minus the lower limit will have another minus sign, so it'll make it positive. L over 2, again, L over 2 divided by hypotenuse. Again, hypotenuse is A squared over L over 2 squared. This side, same thing, all right? Okay, so we have two of those. Get rid of 1/2 and L cancels over here, this L's. So the electric field, which will be to the right, is equal to Q over 4 pi epsilon 0 A 1 over A squared plus L over 2 squared. All right, something like that. That's your electric field to the right. Points to the right. You can write it as an electric field with the unit vector, if you like. Okay, it's pointing to the right. That's an exact formula. If you know the length of the rod and how far you're from that rod, you know exactly what the electric field would be. All right. Now, let's consider some limits. Like what if you're so close to the rod that this looks almost infinitely long, okay? So that would be the limit. Consider the limit when A is so small, capital L is so greater than A. Okay, that symbol here, double greater than, it just means that A is so small compared to L. All right, so what do I do then? This is practically means infinitely long cylinder, all right? So I'm gonna use an approximation. You guys know the binomial expansion, right? Binomial expansion. I mean, it can be applied to a plus b to the power m or something, but in general, you can reduce it to something like this. So 1, if x is small, if x is small, this will be 1 plus mx, okay? I mean, you can actually continue the expansion if you like, m times m minus 1 over 2 factorial x squared. We're not going to go there, but you know how it goes, right? It's a series expansion for small x. You can find it from binomial expansion or from Taylor series or whatever. So let's just consider these, ignore the x squared. Let's just look at this one here, 1 plus that, okay? So if you apply that to this function here, how am I going to do that? I need a small number. I know a is small, much smaller than L. I know that. So if I take this L, right, if I take this L out, so here, 1 over a squared plus L over 2 squared. What if I take L over 2 out? So 1 over L over 2 times, right? So that 2 goes with A now. So I will have 2A squared plus 2A over L squared plus 1, something like this, right? Okay, so using this approximation then, this is equal to 2 over L times 1. Okay, M is negative 1/2. And X is like a 2A over L. I hope it's not getting too much complicated, but basically I'm doing this so that I can get rid of A over L. Remember, A over L will be very small, so I can ignore this. Ignore that. What is left? 2 over L. So A will be Q over 4 pi epsilon A. Okay. I wanted to get rid of L really. So, oh yeah. There's 2 here. L. So, okay, so this 2 cancels here. So here's what I'm going to do. Remember there was a density here? Density was Q over L. If it is infinitesimally long, okay, doesn't really make too much sense to think about Q anymore and L. Just keep things in terms of lambda, all right? So I'm going to take this Q over L and simply call it lambda. So here I have then, let me get rid of this, I don't know what this, okay. Then I will end up with lambda divided by 2 pi epsilon 0 A. Okay, so that would be the electric field near an infinitely long linear charge distribution, where alpha is the uniform charge distribution. Okay, so this should be in your book somewhere. Actually, you know what? Let's double check if I got it right. Infinite line of charge, lambda over 2 pi epsilon 0 r. Okay, in the book you have r, I have a here. Okay. Okay, so that's the answer. This is the electric field. Let's write it in the vector form. The electric field when you're so close to the charged object that it looks like it's infinite, you don't see the end, okay? A virus really close to the thing doesn't even know that it has its ends. It thinks it's infinitely long, right? So in that case, this would be your answer. Lambda over 2 pi epsilon 0 a. This is the x direction, right? I hat. So this is your final answer for that limit. So infinitely long charged object, and you're standing A away from it, then the electric field will be radially outward. Of course, if you're on the left-hand side, the electric field would be to the left, all right? Now, one good thing about this infinitely long object is you can forget about symmetry now, okay? You can move anywhere vertically. There's still equal amount of charge above and below because it's infinitely long, remember? And you can stop worrying about symmetry. It's only valid for finite size objects. For an infinitely long wire, you don't have to worry about that vertical position. But if you're to the right, radially outward means the field will be to the right. If you're on the left, radially outward means to the left, but it's in 3D. So if I look at this pen from above, this is what I would see, the top view. A positive charge here. I have radially outward field lines. Okay? But here's the magnitude, lambda over 2 pi epsilon 0 a. Now that's only one limit. What about the other limit? Let's call it number 2. Number 2 is the opposite. In this limit, A is much greater than L. You're so far away from this object. You're so far away from the object. What happens to the electric field? What happens to the electric field? Now you can work it out mathematically, just like I did. Instead of factoring L, you can factor A out, and you'll be done. Or, actually, you can just get rid of L right away. So let me do it. I was going to say, or think in terms of physical arguments. If you're so far away, I mean, this is like, I don't know, 7 inches long, but you're 5 kilometers away. Excuse me. This looks like a point, right? It becomes like a point charge. So you could simply use your old formula. Let's prove it, though. So this formula above, Q over 4 pi epsilon 0 A, 1 over square root A squared plus L over 2 squared. If L is so small compared to A, L squared is so small compared to A squared as well. So you can ignore this term here. Just ignore it. It goes to 0. Oops. It goes to 0. Ignore it. So what is left? 1 over square root A squared, which is 1 over A. You have another A here, A times A squared. So you will have Q over 4 pi epsilon 0 A squared. So if you're really far away, you're all the way here, A is so large, this looks like a point particle. All right? So it doesn't really matter if you're here, or if you're there, or if you're up here. If you're A away from it, you know, it doesn't depend on your orientation, but if you're A away from it, and A is so large compared to the size of the object, it starts looking like a point particle. Indeed, you have here the I mean, this is the 1 over 4 pi epsilon 0 constant, right? K times Q over A squared. You get the old formula back. Okay, so please try to understand these considerations. Once you find your answer, you can always continue. I mean, the answer is here. Okay, this is the answer for an arbitrary L and arbitrary A. That's your answer. It's to the right because there's symmetry and all. But then you think about the limits. What happens if you're so close to the object? What happens if you're so far from the object? And those are your results. Okay, so that's one of the examples I was planning to talk about. The other one is see, we did the linear. Let's do one with area now, all right? And maybe before we do that, let's take this and bend it and make a hoop out of it. Okay, a circle. Let's start with that. So in this case, the charge distribution is a ring. Okay, here's your ring. The total charge here is Q. The ring has a radius R. And you are a distance, what do you want to call this? Let's call it A again, doesn't matter, A. And you want to find the electric field, all right? Now, this is a positive charge. We can still work with a linear charge density, lambda. A linear doesn't have to be a straight line, because you can take a straight line and bend it and make a hoop out of it, right? So the total charge Q would be distributed along the circumference, which is what, 2 pi r. 2 pi r, right? That could be your linear charge density. If that is your linear charge density, what is the charge contained in a small portion of that? So if you take a small arc here, a very tiny, okay, I'm exaggerating, a very small one, which corresponds to a small angle here. Okay, my drawing is really bad here. What I'm trying to draw is this. You have a circle, all right? So circle of radius R, and then a very small angle, infinitesimal angle, d theta. Then there's an arc length here. Okay, I'm exaggerating still, but that's what I was trying to draw over here. The arc length of length ds, which is equal to r d theta, right? I mean, you know this from circular motion and all that. If the total charge Q is uniformly distributed along the circle, then the charge that corresponds to this, which I'm going to call dq now, will be equal to that density, lambda, times the length. All right, so dq will be the charge density Q over 2 pi r times r d theta. R's cancel and all. So that's dq. So because of that dq, we'll have now an electric field right here. Connect the dots there. At this point here, you will have an electric field that points this way. I'm going to call it dE. Okay, same idea. I'm using the same principles I did in the previous example. It's just for a circle now. Like this is an angle here. I don't know, what do you want to call it? Phi. And here another angle, the same angle, phi. All right, and then I probably need dE cosine phi. Why? Because if you take this and then go around the circle, say if you're over here, then there's another dq there with the same magnitude, right? I mean, then you will have a dE that way, but those will have a y component that will cancel the other y component, but the x components will add. Okay, same idea. That's why I need a dE cosine phi thing there as well. So this is r squared plus a squared, right? That's the hypotenuse. Here you have the right angle. So that dq divided by r squared plus a squared multiplied by 1 over 4 pi epsilon 0. That's what dE is. All right? So I'm going to multiply it by cosine phi, and then I'm going to add the contributions from each little dq, which means I'm going to integrate over the variable theta, and the theta will vary between 0 and what? 2 pi. Okay, so let's write it down. 1 over 4 pi epsilon 0 times dq, dq is right there, total charge over 2 pi times d theta, 1 over r squared plus a squared, and then cosine phi. Cosine phi is a over that. A over square root r squared plus a squared. And I'm going to integrate this. And this time, integral is even simpler because I'm not integrating over r or a. These are constants, right? I'm only integrating over theta from 0 to 2 pi. All right, so the integral, okay, something's happening to the video here. I don't know why. Okay. The integral will be simply 2 pi. From here, I will have 2 pi, which will get rid of that 2 pi. So this will be equal to, do I have any other cancellations? We'll see. So q times a divided by 4 pi epsilon 0. It's so easy to miss a factor here, okay? You've got to be careful. I mean, I've done it a million times, but I still make mistakes. So you've got to be very careful. So you don't want to drop any variable along the way. R squared plus a squared to the power 3/2. All right? After you get rid of 2 pi's. Let's double check. 1 over 4 pi epsilon 0 from the formula. dq is q over 2 pi. Okay, r canceled. Fine. Okay, good. It looks like it's okay. So that's the answer. All right? That's the answer. What happens if a is 0? When a is 0, you're at the center. When you're at the center, these electric field vectors are like that. For every vector here, there's another one there. For this one, that one. They all cancel out. So the field is 0 at the center of the circle. And it makes sense because if you take a, 0, here, 0 times q is 0. So when a is 0, e is also 0. What is the other limit? When a is much greater than r. What happens then? Okay, let's do the same trick. Let's factor a out of the 3/2 thing there. So qa over 4 pi epsilon 0. Now a squared to the power 3/2 gives you a cubed, right? So here you will have a squared is out, 1 plus r over a squared. Okay? So r squared over, if I factor a squared out, I get that. Now, r is so small compared to a, which means I can ignore this. It goes to 0. So what is left? A cubed, right? I mean, there's 1 left here. 1 times a cubed. There's an a in the numerator. So get rid of this 3, make this 2. The answer is actually something you already knew, right? A squared, just like in the previous case. If you're really far from that circle, the circle appears like a dot, a point charge. So you get back q over 4 pi epsilon 0 a squared. Okay? You get the original formula. So it checks. All right, so what do we do now? Area. I was talking about area, okay? So let's take this result. Now, this was before the other 2 extreme cases. This is general result. And let's apply this to not a circle, but a disk, okay? So I'm gonna move downward like this. I'm gonna put this where I can still see it. So now I'm gonna take a disk instead of a circle. This is a disk, but a uniformly charged disk. Charges everywhere on the disk. Looks like an egg, but it's still 2-dimensional. Okay, it's not an egg, it's a disk. On that disk, I'm going to consider a small charge. Why? Because I want to find the electric field right here, which is A away from the center of the disk. I want to find the electric field there. Okay? Now, let's think in terms of area density, area charge density. It's a uniform distribution, therefore sigma, that's what it is equal to total charge divided by the area of the. Now I use r here. This r is the radius of the disk, okay? Pi r squared becomes the area. So q over pi r squared is the charge density. Good. Now what I know is this over there. That is for circle. So I'm going to consider a circle around the center, a ring. This is a ring, a very tiny ring, but it carries some charge on it, right? That charge will be my dq. Now, how do I find dq in terms of sigma? How do I write dq in terms of sigma? Sigma is the area charge density. If I multiply the area of this blue ring by sigma, I get the charge. We call it dA. dA is the infinitesimal area. Here, this shaded area. If I can draw it here, maybe bigger, you'll see. This is the ring. This area of the strip. How can you find it? There are 2 ways of finding it. You can either subtract this area from the bigger area. That's one way. You can either, okay, this radius is now little r, okay? You can either subtract the smaller one. Now by smaller, I mean this. This is a very tiny strip. So the area is, the thickness is dr, okay? A very small increment along the radial direction, dr. So you can either subtract the area of the small one from the larger one, so pi r plus dr squared minus pi r squared. You can either do this, or you could imagine you cut this and open it up. If you did that, you know, take a pair of scissors and open this up, and you will have this with thickness. A rectangle is what you're going to have, dr, and the length is 2 pi r. So the area of a rectangle is simple. It's just one side times the other one. So dA would be 2 pi r dr, right? Now, can you get the same thing from the above method? This is either or, right? Let's try it. So if you expand this, pi r squared plus 2 pi r dr plus pi dr squared minus pi r squared. This pi r squared cancels that pi r squared. Now 2 pi r dr is already here. That's what we had in the other one. What about this? Dr squared, okay? It looks like we got two different results, but no. Dr is already very small, infinitesimal, okay? There's nothing smaller than that. So dr squared, we can ignore. If dr is so small, dr is so small. Dr squared is so small, so ignore it. So the answer is 2 pi r dr. Okay, so no matter how you look at it, you get 2 pi r dr. That's your area. So you just plug it in here then. dq will be sigma, which is q over pi r squared times dA. That is 2 pi r dr. Get rid of pi's if you like. So that's your dq. Now take that dq and then plug it in the formula for dE. Let's remember what we did before. Over here, right there, okay? So replace the charge here with what we found. Everything else is the same except for capital R will be small r. Okay, so Q, instead of Q, I'm going to use QR dr over r squared, that's dq, times, what was it, A? Let me look at it again. Times A divided by 4 pi epsilon 0 times, or divided by, r squared plus a squared. Of course, I'm going to replace the capital R by small r, little r, times plus a squared to the power 3/2. So if I can integrate this over r from 0 to capital R, I get the electric field. Okay? See, I already know that it's pointing in the x direction. It doesn't have any vertical component from the previous problem. If those rings, concentric rings, all have electric field in the same direction, they add up. There's no reason why there's a change in the direction. I can simply integrate this and I'll be done. Okay? So this is equal to QA over 4 pi epsilon 0 r squared from 0 to r. I forgot a 2. There was a 2 here, remember? 2. There's a 2 here. I'm glad I saw that. So 2r dr divided by r squared plus a squared to the power 3/2. Okay, now a simple substitution. r squared plus a squared, call this something else, call it y. And then 2r dr will be dy, right? So this integral will become dy divided by y to the power negative 3/2, okay? So, negative 3/2 dy, you raise the power by 1 and divide it, so y to the power negative 1/2 divided by negative 1/2. So, electric field is now equal to negative 2 times Q times A divided by 4 pi epsilon 0 r squared 1 over square root y. 1 over square root y, or 1 over square root r squared plus a squared. The limits. Okay, so when r is 0, when r is 0, y is a squared. Sorry, when r is 0 here, and then r goes to capital R, the upper limit. All right. Okay, so final stages are now. We can get rid of this 2, I guess. Why don't I do the same trick by switching to sigma again? It is useful, you know. So I'm going to take this q over pi r squared was sigma. 2, 4, 2. So negative sigma over 2 epsilon 0. Now I can plug in the limit. 1 over square root r, capital R, I mean, plus a squared minus 1 over. Now if I plug 0 for r, it's only a squared, so left. So square root of a squared is a. This is what I get. Okay, so that's the answer. Let's take a look at the limits now. Limits. The first limit, that's when A is so large compared to R. Okay, you're so far away from the disk. Will it look like a point particle? Let's check. Then E, if R is negligible with A, okay, now I think, is there a mistake now? Okay. I don't want to get 0, right? I don't want to get 0. Okay, let me check this answer from the book. There must be, okay, 1 over x. It looks like we got it right. Oh no, there is an a missing. Oh yeah, I forgot the a. Remember, there's an a up there. Okay, there's an a. Good. This a, we forgot to carry this a here. All right. So in this limit, what will be the answer? So let's do the same trick. Do I still get 0 there? I don't want to get 0. I don't want to get 0. 1 over r. This is the correct, okay, formula. Let's factor A out. Maybe I'll see it better if I do that. Let's factor A out and then maybe get rid of the negative here. So this will be sigma over 2 epsilon 0. Then there's only 1 left here. 1 minus 1 over. Now remember, we're taking A out. So this will be 1 plus R over A squared. Okay, so this is after factoring out A. Now, if A is much larger than R, oh, okay, I know what I'm going to do. Okay, I need to use that expansion again. I need to use that expansion. Remember, 1 plus R over A squared to the power negative 1/2. When R is so small compared to A is equal to 1 minus 1/2 R over A squared. So I have here 1 minus, this one I'm talking about, minus 1 minus 1/2 R over A squared. Okay. So if I do that, this one cancel that one, but what is left here is plus 1/2 R over A squared. So sigma over 2 epsilon 0 times 1/2 times R squared over A squared. Now this looks weird, but it's not. Remember what sigma was? Sigma was pi over, sigma was Q over pi R squared. So that's equal to Q over pi R squared. Now 2 times 2, 4. 1 over 4 pi epsilon 0 times R squared over A squared. R squared cancel. This is the, I already use pi here. This is the K, electric constant, then Q over A squared times electric constant. 1 over 4 pi epsilon 0, or Coulomb's constant, Q over A squared. That's what I expected, right? If I'm really far away from the disk looks like a point particle. That's the first limit. What about the second limit? Okay, limit here, limit. When A is so small compared to the radius of the disk, you're so close to the disk. The disk looks infinite. That's what it means. In that case, if A is so small, all right, now I have to use the approximation the other way around. All right, so if A is so small, what happens? If A is so small, here you have 1 over very small number, which becomes infinite, right? So this whole term goes to 0. In this limit, 1 over A goes to infinity, or very large. Therefore, that factor, what is it? 1 over square root 1 plus R over A squared goes to 0, okay? If the denominator is huge, it goes to 0. Therefore, electric field goes to sigma over 2 epsilon 0. Now, this is probably the craziest results we've ever got today. Why? Because it doesn't depend on A, okay? This does not depend on A. It's a constant. So it doesn't really matter if it was a disk or a rectangle rectangular plate, right? It could be any shape. If you're so close to the object, the electric field has nothing to do with the outer boundaries. All right, this could be a disk or a square or rectangle, doesn't matter at all, because if you're so close to the object, it looks infinite. And this, sigma over 2 epsilon 0, that is the electric field. It's outward. All right, it's perpendicular to the surface, pointing outward if it's positive charge. If it's negative charge, it's pointing inward. But it's a constant, okay? It doesn't depend on A. So let's stop this topic here. Let me talk about dipoles, and that will be done. Okay, so these are in your book, okay? Please go over the examples in the book if you want to. They have exactly the same numbers, examples. And I'll do problems in class, different problems, different configurations. Let's change gears now and talk about a dipole, okay? Dipole. What is a dipole? Di means two, right? So we're talking about two charges. Pole, like point charges. So imagine you have a point positive charge. Let the other one be a negative charge. And let these be separated by a distance d. D is the separation between these two charges, okay? Now, how can you make it? You can take a toothpick, okay? A toothpick is not a conductor. Good. Put a charge on one end, another charge on the other end. You have a dipole, all right? That red line is actually a vector. A vector, D vector. Goes from the negative to positive. All right? And the charges are Q. Positive Q and negative Q. Let's say they have the same charge, magnitude-wise, but say opposite sign. A dipole is a vector which is made of these two charges, okay? Now, whether you have a physical object between the two charges or not doesn't matter. What matters is the distance between the charges is fixed, okay? Then the dipole, we're gonna call this P, okay? This is a dipole, and the letter P, there are many things in physics with P, right? Like power, momentum, all right? Please don't get confused. This is the dipole moment, actually. It's called dipole moment. But this is nothing but a vector made of the original vector D and the charges Q. So you just multiply Q by this vector D. All right, that's your dipole moment. Now, in some books, you may have it as a 2QD. That's because they take the distance from the center, okay? Same idea. So in my case, I called it D from one charge to the other, so it is still Q times D, okay? It's called dipole moment. Now, why do I need this? Okay, going back to the toothpick with two charges. Now, what if I place this inside a field, a background field, all right? There's already a field, which I'm going to show with the blue here, an existing field, electric field, let's say pointing this way. This is the electric field, you know, and then the two vectors, you know, make an angle theta, right? Something like this, theta, the situation. So according to the basic relationship between the Coulomb force and the electric field, I'm expecting to have forces on these two charges. I know that. Now, if the charge is positive, the force points in the same direction as the electric field. But if the charge is negative, it flips the direction and starts pointing in the opposite direction. Force. So what do you think is going to happen if you have forces pointing in the opposite directions and it's on the edges, right? You'll expect this to rotate, right? There's a torque now. It's as if the midpoint here becomes the pivot point. And then you can think about the line of action. Remember the definition of torque. You consider the line of action and find the shortest distance between that line of action and your pivot point. Okay, so this is line of action, line of force, whatever you call it. And this becomes the pivot point. The shortest distance between the pivot point and that line, which is called the lever arm. And how do I know if it's shortest distance? Because this is 90 degrees now. This becomes the lever arm. Okay, that lever arm can be found easily. See, this is theta, right? Theta, theta. So hypotenuse is d over 2. So d over 2 sine theta is the lever arm. You multiply the lever arm by the force, you get torque. But that's only because of the positive charge. For the negative charge, you also have another equal amount of torque, so multiply this by 2. Net torque on this object will be, at that instant, because it's going to start rotating, will be equal to, after we get rid of the 2's, sine theta d q e, okay? All right, so that's actually nothing but the cross product of the dipole moment with the electric field. You can always change it, check the direction with the right-hand rule, if you remember it from Physics 1. Now, you either think about the rotation. In this case, it's like a clockwise rotation here. So you curl your fingers in the direction of rotation, and thumb will tell you which way torque vector points at, which is into the screen now. That's one way. Or use the 3 fingers of your right hand and put your thumb in the direction of P, and then index finger in the direction of E. So I'm doing right now, you do it as well when you're watching this. D cross E, middle finger points to the screen, into the page, right? Into, so this is the direction. A cross in a circle means into. A dot in a circle means out of. Out of page, into the page. In this case, it is out of the page. I'm sorry, into the page, right? Cross. That's the direction of the torque, all right? So that's the torque. Now the maximum torque is, of course, when theta is 90 degrees. And the minimum torque is when theta is 0. The T is 0, right? Tau is 0. So if the dipole lines itself with the electric field, it's done. There's no more torque. Okay? But what happens is if you just try to make this, with real materials, charges, toothpicks, and the electric field, it's going to rotate, but it's not going to stop at the electric field. It already has momentum, right? Angular momentum. It's going to continue. It's going to slow down, come back, oscillate. It's going to start going under a simple harmonic motion, right? And when it's doing that, it's going to have a kinetic energy, right? But since the rotation speed changes, this kinetic energy also changes. So how does that work? How does it work in the context of energy conservation? There should be a potential energy. And I'm not talking about gravitational potential energy. I'm ignoring gravity totally, because gravity is so weak when electric forces are considered. What I really consider here is the electric potential energy in a way. This is the potential energy of the dipole, all right, when it's placed in an electric field. So it's going to find the minimum potential, and it wants to stay there or oscillate around the minimum potential, let's say. And you can find the expression for that potential. All you have to do is to find out the work done by the torque, right? So this torque changes with angle. So the infinitesimal amount of work done by the electric field in this case would be tau times d theta, right? That's from physics 1, right? Just like in a linear movement, force times distance is work. Rotational motion has torque times angle work. You can integrate this from theta 1 to theta 2, right? And then you have to take an expression for tau from there. See, tau is into the page, a rotation clockwise, but our theta increases the other way. Therefore, you can write tau as negative, negative sine theta, q d times e, all right? And then you add a d theta to it, and then you integrate this from some theta 1 to theta 2. If you carry this integral out, of course, the integral of sine theta is negative cosine theta, right? So you get cosine theta. So you get something like this. You will get the difference. I'm going to call it U now for potential energy. U2 minus U1, or delta, negative delta U, where U is Q dE cosine theta, okay? Cosine theta 2, or theta for each. So I will have Q times D times E times cosine theta. Can you see what this is now? Remember, when we had the sine theta, we had the cross product. Now we have the cosine, which means we need the, there's a negative here also, we need the dot product. So negative P dot E. Okay, this is your potential energy. Okay, I'm going to stop here. We finished that chapter pretty much. The torque and the potential energy. So the dipole itself has its own electric field, obviously, which I didn't do here, but if you want, you can calculate it. Now you know how to calculate the electric field for a given charge distribution. you have the true charge here. You can find the electric field due to the dipole, not the external field that I used here, but the field due to the dipole. You can also find it if you want, okay? And that's in the book. So, all right, this finishes this chapter. And in the next video, I'm going to be going over Gauss's law. Okay, electric flux, Gauss's law, and then applications. All right? Okay, I'm going to stop recording now. See you next time.